of 316L processing, heat treatment, and the consequent microstructure. Okay, compared to conventional manufacturing, DED introduced extremely high cooling rates and directional solidification, leading to anisotropic microstructures. This is fundamentally a non-equivalent solidification process, unlike traditional metallurgy. Energy density. Energy density is a key controlling parameter in DED as it determines melt pool stability and defect formation. Too low leads to lack of fusion, while too high leads to keyhole porosity. Therefore, DED operates with a narrow process window. Okay, let's go ahead with process window. The defect type is directly governed by the energy input state. Defects are not random, they are energy state dependent phenomena. Okay, three scale microstructure. This at a micro scale, columnar grains grow along the build direction due to directional solidification. At the micro scale, cellular and dendritic structures form with high dislocation density, which contributes to strength. At the nanoscale, oxide inclusion are present, while harmful MNS inclusion are largely absent. Together, those features give DED 316L its unique combination of mechanical performance and corrosion resistance. Residual stress originates from thermal mismatch during rapid solidification and repeated thermal cycling. It can reach near yield magnitude and strongly affects fatigue performance. And the sigma phase. The sigma phase forms in 600 to 800 Celsius range and significantly degrades ductility and corrosion resistance. This is a critical metallurgical instability region for 316L. Okay, heat treatment strategy. At around 400 Celsius, recovery occurs with minimal microstructure change and moderate stress relief. Between 600 and 800, additional stress can be relieved, but there is a risk of embrittlement due to phase precipitation. At approximately 1100 Celsius, solution annealing provides the highest stress relief and full recyclization, but it also causes softening. Therefore, the heat treatment temperature should be selected based on desired balance between stress relief and mechanical properties. Okay, and annealing effects. At around 1100 Celsius, full recrystallization occurs, removing residual stress but also coarsening the microstructure. We gain isotropy but lost fine scale strengthening. Yield strength is controlled by microstructure, while ductility is controlled by defects. This separation of mechanisms is crucial for engineering design. And DED 316L shows improved corrosion resistance due to the absence of MNS inclusion and rapid pass film formation. This is particularly important to chloride-rich environments. Extend life in corrosive environment. In air DED 316L and conventional 316L show comparable mechanical performance. However, in corrosive environments such as 3.5 NaCl solution, DED 316L exhibits significantly higher strength and durability. The key reason lies in the corrosion fatigue mechanism. In chloride environments, pitting corrosion acts as the primary source of crack ignition. Due to its superior resistance to pitting corrosion, DED 316L delays crack nucleation. This significantly extends the fatigue life of the material. Optimizing DED 316L requires a balanced approach across multiple factors. First, the hierarchy microstructure provides a strong foundation for both mechanical strength and corrosion resistance. Second, there is always a trade-off processing. Higher energy input improves productivity, but increases the risks of the defects. Third, Heat treatment must be carefully selected depending on whether stress relief on strength retention is the priority. Most importantly, microstructure controls strength, while defects control failure behavior. This makes DD316L particularly advanced in corrosive environments such as marine and chemical applications. To optimize DD316L, we must consider process parameters, microstructure, and surface integrity as a combined system. And overall, the best performance is achieved by balancing processing structure and surface condition. Thank you for listening.